Brilliant. Thanks, Kevin. Good afternoon, everyone. Welcome to the latest Talmo seminar series. We're absolutely delighted to have John Mason from the Open University joining us for this. Before we start, just to highlight, we are going to be recording this particular session. So if you don't want to be identified, do sort of change your name in any of the sort of identifiable sections on the software. As Rachel mentioned, please do post any comments into the chat function. We'll be keeping an eye on that. Please do make sure it's set to all presenters and attendees to make sure your views are fully shared. And we'll be using the Q&A functionality. So if you've got particular questions that are different from sort of the general chat, please do post things into the Q&A. What we'll do is we will kind of go through some of those, pull out some questions, and we'll ask John a number of your questions at the end, because I know there'll be a number of those, because John's brilliant at getting us thinking about teaching mathematics. The next event comes around really quickly, which is on Monday. So over the weekend, a link will come around to, if you want to join a workshop that's been put together, particularly by colleagues within the Royal Statistical Society, the education group there, on the teaching and learning of mathematical and statistical computing. So that's that's an afternoon event with a number of sessions embedded within it, and that's looking a full and exciting program. So we'll send details around there. And then finally, I think we're continuing to add resources. I know that I point the Talmo resources to colleagues in Birmingham quite a lot. There really is a growing wealth of material on there, and I think there's a lot of thanks due to Kevin for pulling all that together. But also, some of the people that I know are at this webinar have contributed things, and made them available to other members of the community as well, which I think shows why the mathematics community is so great. So have a look, see the resources that are there, past resources from these workshops, but also things that other people have produced. If you've got anything that you want to share with other people, do send it across to one of us, and we'll look and see if we're able to make it available. But I think that's probably enough for me. I'm just the warm-up act here. The main act is John Mason, who I think really is one of the legends of mathematics education. He's worked in, John may shake his head, but John is one of the few people whose seminars and talks that I've been to, where every time I come out asking questions about how students learn mathematics, and I think John's sessions are guaranteed to get us thinking. I think open book online assessment is something that we're all going to grapple with. I don't think it's the case that anyone can tell us exactly what we should do or how we should write our own questions, but I know that John will be brilliant at getting us to think about what we're asking students to answer or understand, and also the implications for how we go about teaching some of our content in an open book environment. So I know that this is going to be a fantastic session from a fantastic individual who's done some great things in maths education. So after that build up, John, no pressure, over to you.
Thank you so much, Michael. Now I need to continue. Share. So I'm hoping you can see my slides. Good. So first of all, thank you ever so much for inviting me to do this, because it's given me an opportunity to have a good think about it, and to reflect back on things that I learned in my 40 years at the Open University. These slides are all already on my website, and they'll be available through Talmo. I want to point out that usually I offer people little exercises to engage in, to think about, and then to give me responses, and that's clearly not going to be possible with so many people. So what I intend to do is to offer pauses at various points, and the purpose of the pause is for you to be thinking about whatever it is I've either said or asked. In fact, pausing is an interesting device to be using even in a live session, getting students to learn what to do when I pause, and what I want them to be doing when I pause is thinking through what it is that's just been said or just been asked. And I find that a real, really useful device when I'm teaching. Anyway, that doesn't, oh, that's interesting. How do I make it? Oh, gosh, okay. So, understanding and facility. Presumably what we want people to do is to understand mathematics. So one of my questions is, what does the word understand actually mean? It's a very peculiar word. It's curious because originally it meant to stand among, presumably to stand among a group of people, all of whom had a similar grasp or understanding. So the word is sort of self-referent. But now it's being used to mean to perceive the meaning or explanation of something, to have sympathetic awareness of something, to be conversant or familiar with something, to have mastery of something, to realize fully, to appreciate. And whenever I run up against a word like understanding, where I lose a grip on what it really refers to, I find it's useful to replace it with some other words. And so I'm going to use whenever I remember to, the words appreciate and comprehend, because these speak more directly to my experience. So there are various aspects of a topic which I can appreciate because it's about their use. There are various other aspects that I comprehend. I can do things with them. And this will all emerge as we go on. Now, it seems to me that facility is something quite different, and that's to do with performance. So I will talk about facility in relation to appreciation and comprehension. Now, I think it's worth starting with this. It might be assumed that open book testing cannot include facility because candidates can look things up in real time. However, evidence is not in favor of that conjecture. Edinburgh is a very good source for experience in this, and their experience mirrors some of the experience I had when I was an undergraduate and a graduate student. Open book makes far less difference to overall results than you might expect, because students who've not engaged with the material may not even be able to find the appropriate section of their book or notes explaining a relevant method. If you spend a lot of time shifting through the pages of a book, you're not actually going to do anything on an exam. And it's almost impossible to use or other course materials successfully in an examination without properly studying these beforehand. Yep. Observations show that students tend to use materials brought in to examinations relatively little and mainly as a check. So that seems to me to relaxes my thinking a little bit about open book examinations. But the question is, what do we do about being online? So this makes me ask questions, because if I'm hoping that students will understand something, what on earth do I mean by that? So the question I want to ask you to think about for a minute or two is, what do I want students to get out of my course? I'll pause for a bit. Now, I'm confident that there are lots of ideas that you've got that I haven't thought of, but here are some of the thoughts that came to me as I addressed this question. Do I want them to have competence in the use of technical terms? Do I want them to comprehend concepts? And what does that mean, of course? Do I want them to have facility with procedures and techniques? Do I want them to comprehend particular proofs or proof in general? I cannot resist telling a few anecdotes. I remember my measure theory course as an undergraduate, and the examination, I was able to predict some of the questions because the person giving the course had given it for so many years And we had all the past exam papers, and you could actually work out the cycles for various of the proofs. So I memorized, because I had to memorize the proofs of various theorems, some of which actually did come up. And so I was able to put them back on paper for him to read, which seems to me to be nothing to do with comprehension whatsoever. And it was only years later when I began to realize that I had some comprehension of what measure theory was actually about. Do I want to expose people to particular proof techniques in my course? Do I want them to appreciate places where the topics in the course have been used outside of that particular topic? And for all of these, and for any of the other ones that you've thought of, the real question is, what constitutes evidence of these? And if I'm thinking about evidence, and seeking evidence, I need to ask myself, what experience have the students had which is pertinent to the things that I want to get evidence of? So it's unfair, for example, to ask on an examination a kind of question which is completely different to any of the questions that have occurred or any of the topics, any of the discussions that have come up in class or in the teaching sequence. So this leads me then to address questions about the list that I've got. Namely, how do students encounter these explicitly in my teaching? So, meaningful use of technical terms, and not just by me, but by them. How do I get them in class or in the process of their study to make meaningful use of technical terms? And we'll come back to this, I hope, in an example. What is it that I do in my classes, in my teaching? I keep using the word classes. Anyway, in my teaching, that means that they have experience of what it means to comprehend a concept. It's not enough for me simply to keep using a concept, even to proving theorems and lemmas and constructing examples and so on. But do students really appreciate the totality of what's involved in comprehending and appreciating a concept? In my teaching, how do I help them gain facility with procedures and techniques? I can assign a bunch of exercises, but it's not the doing of the exercises which gains facility. It's more subtle than that. How do students encounter from my teaching what it means to comprehend a proof? Just because I've been through the proof, I may have even interacted with them at different stages of the proof. But do they have any sense of what it means to comprehend a mathematical proof? How do I draw attention to various proof techniques? How do I indicate that it's a technique and not simply a one-off way of proving a particular result? This relates to one of my major interests, which is the whole role and structure of attention, the structure of the teacher's attention, the structure of the student's attention, and how these interact. But that would be for another time. How do students gain appreciation of places where topics have been used? And used by them, not just by me or my claims. One of my favorites was when asked, what was the question? Why are we doing this? Or what's this topic really? Why are we studying this topic? My response for a long time was to say it's absolutely essential in the steel industry. That was at a time when we had a steel industry. And I could tell from their faces that that was not that was not the question they were asking. That was not the kind of answer they wanted. What they were really trying to tell me was, we don't really appreciate or comprehend what's going on here. So let me take a simple example. I'm going to take something that belongs really in A-level maybe, or in first year foundation course, but that's so that people from different topics, different mathematical disciplines can appreciate. And the whole point is that this is an example, And so the invitation is for you to be thinking in terms of some topic that you're teaching or you're preparing to teach, and use absolute value of X as a placeholder. So the question I would like to say to students is, show me that you appreciate, comprehend, and have facility with absolute value of X. I would love to see what teachers, what students would offer me. But of course, they would have to have had prior experience of what it is I think appreciating and comprehending and having facility really means. So here's some more precise. Under definitions, construct 3 examples to demonstrate how absolute value of X works as a function on the reals, and 3 for the complex numbers. I'm pausing for you to just think what that entails. One of the things that my wife and I have discovered in mathematics education is that the role of examples. From the earliest records of the teaching of mathematics, examples have played a key role. But the question is, what do people do with examples? And here we're asking people to construct, let's say, 3 examples about some concept. Under the concept image, a notion introduced by David Tall and Shlomo Wiener, which includes all of the associations, all of the links, all of the images that people have and that associate with a particular topic, in this case, the absolute value of X, mod X. And so here I can ask people, draw 3 different diagrams associated with mod X and state in what way they are different. I'll explain why I put that latter bit in a minute. Have a just a little think. What would 3 different diagrams look like for you? Well, I'm going to offer you 3. They may easily not be your 3. That's fine too, of course. And you may have some other much better ones than I have. Whoop, oh, hang on, they're supposed to, oh, I don't know when it's going to come up. The diagrams will come up at some point. My slide is not doing what I thought it was going to do. Oh, there it is. Okay, here they come. So that seems to me a plausible diagram that I have in my mind, I have access to when somebody says mod X. There's another one in text that requires a little bit of interpreting, a little bit of reading. Putting those 2 together might lead you to something like that. And that led me to give a 4th one. You can see the sort of course that I am imagining that these students are taking. But that 4th one is perhaps not a diagram that any students will have actually seen. I don't know. I've never seen it in a textbook. But I'm trying to indicate that I'm interested in the region where the absolute value of X minus A is less than delta. Right. So to do now with manipulating absolute value of X plus Y, etc., is an absolutely important classic relationship. But what I can ask them to do is to provide 3 different contexts from the course where this is actually used. Now that open book exam, they would, be able to go through their notes and find 3 of those. But if they knew that this kind of question might come up, they could prepare so that they've got some ready. They don't have to sort of search through and look for the symbols on the page. They can be doing it intentionally. Now, it might be that in the course notes you provide reasoning going both directions, but I was guessing that perhaps that doesn't always happen. And so here's an opportunity to get them to reason in the reverse direction. And Now, I guess it's quite possible that this might be somewhere in the notes, but if a student has to be looking through their notes for such elementary narratives, ideas, then they're simply not going to make it through the rest of any examination that you're going to offer them. But what's important here is I'm trying to provoke students to be thinking about a narrative, a story that they tell themselves when they use absolute value of x minus y is less than or equal to, etc. So I'm trying to promote students developing the notion of a narrative. And I added these just this morning. What about some graphs using the concept? So we know I tried to make one that would be slightly unusual, unfamiliar. So asking them to graph that. And another kind of question that's available, it seems to me, is what is wrong with, and then you propose a graph of a function, and you give the function, of course, and the proposed graph, and ask them what isn't right about this. Now, they won't have that in their notes. They would need to have experienced someone doing a couple of questions like that, so that it isn't completely shot out of the dark. But it seems to me it probes your sense of interpreting graphs and interpreting functions. So the source, the origin of these ideas that are on this slide are, for me, to do with the technical terms, the concepts, the core procedures, the proofs and justifications and proof techniques, and the uses of the topic in other places outside of mathematics or within a particular course. So the yellow words in brown provide a sort of a summary of what's used to generate these various ideas to do with mod X. Now, topic webs. To me, constructing a topic web is a really interesting notion. I examined a thesis many, many years ago, which showed that for students who actually stick through a course, most of their topic webs, as they went through the course, their topic webs for a particular concept got richer and richer and richer. Students who tended to dropped out tended to display topic webs that just they changed, but they didn't get richer. They kept being rather restricted. So let's have a think about mod X. What sorts of things would you associate with mod X? Well, it's the obvious to me at least, the triangle inequality, some version of it is critical. The product of the absolute value of a product is the product of the absolute values. These are manipulative aspects of mod X. So I would anticipate that they would show up in anybody's topic web. The notion that absolute value of X can be thought of as the distance from the origin, both in the reals and in the complexes. And they're used to talk about the size of a number. It's used to calculate absolute value of X minus A in analysis in particular. Distance of X from A. Now, what's important about a topic web isn't the items that are put in the topic web so much as the narrative that students have that goes along with each of the connections. So I would anticipate, for example, showing people, getting students to create topic webs and then using one or other, various of the ones that students provide to get other students to give a narrative for the connections that this particular person was displaying. It's about, because comprehending it seems to me to be about having inner narratives that come to mind when the topic or the concept comes to the surface. And that's used to measure the closeness of X to A, especially if you're doing analysis. But it's also a continuous function differentiable on everywhere on R except for 0. It's an example of that. It's an example of a graph symmetric about the y-axis. And I find that as I start to draw topic web, so one idea or one association generates other links. And so, for example, that makes me think of even functions, if perhaps we're talking about those. But also, it's a symbol used for determinant of a matrix and for the norm of a vector. And I'm confident that that amongst us all present today, we could enrich this considerably. But these are the ones that I came up with when I sat down to do this for myself. Let me reiterate. Not every course is going to want to work on absolute value of X, of course. Mod X is really a placeholder for some topic, particularly some concept, particularly ones that you know students struggle with. And one of the features of, yes, I wanted to offer a distinction here between assessing students' performance and gauging student learning. Now, to me, gauging the topic web is a brilliant way for gauging the development of the enrichment of student learning. I'm not sure that I want to use it as an assessment of the student's performance. In other words, if you can't draw a sufficiently rich topic web, then you're not going to get a very high mark. I'm not advocating that at all. But it seems to me once I start asking myself, what is the evidence for student learning? It's really useful to invite them to do topic webs, not just once for a topic or a concept, but several times over time, and to see whether they're getting richer. And if certain ideas don't appear, even though I think that I've talked about them in the sessions, then I can put my attention to how it is I'm talking about them and whether I'm being sufficiently clear and pointed in that direction. Right. So what are some ways for assessing comprehension and facility? I love this question. Of what concepts in this course is absolute value of X an example? Traditionally, we offer people examples, and they're meant to help people appreciate what the concept is about. But now we're reversing it and saying, here's an object that we've been using a lot in the course. What concepts is it an example? And I'm hoping that you're mentally replacing absolute value X by something else, which is a core object in the course that you might be teaching. Then obviously, putting in slightly more complicated manipulations on which intervals is one thing greater than equal to another. So you're offering something which is a slightly more complicated manipulation than you've probably done in the class, in the sessions. Now, how about describe in simple terms that, okay, a high school student because it's absolute value of X, but it might be a third-year student when you're dealing with fourth-year students or even master students, what this particular concept means. This is another one about constructing an example. Using the absolute value, construct an example of a function differentiable everywhere except at 3 distinct points. Notice it's not just one, because that's the classic one, but I've just extended it a little bit in order to make the students think a little bit further, justify your construction. And I came up with this question, which I've never used before. Advise a colleague how to set about graphing a function, like, and in this case, a double absolute value. But the core of the question is, describe a different way to set about graphing it, and comment on which you think is the easiest. Now, if that doesn't reveal the, a real comprehension and appreciation of absolute value of x, I don't know what would. Now, I've been talking about narratives, and I think they are absolutely vital. And so at the Open University summer schools, I used to use the following sort of task. Select a number of technical terms from the course. Now, you can do that. I used to get the students to generate a list, but you could just put some up that you think are important. The task is to construct some mathematically coherent sentences that link these terms together. I guess it's probably worthwhile having an agreement with the students that the following sentence is not acceptable. It's not mathematically coherent. In this topic, we studied, and then term 1, term 2, term 3, term 4, however many there are that you've asked to link. That isn't a mathematically coherent sentence. And I found that students really took to these, and it gave them a sense of what the topic was about altogether, as a whole. Another way to do that is to select 2 technical terms from the course and construct a mathematically coherent sentence that links those two terms together. Again, you'd have to have done this with them in class so that they were familiar with the sort of question that's being asked and what constitutes an acceptable answer. And it seems to me that if I were working online, I could choose those randomly for each student online. So there would be no use to them communicating with each other. Yes, they could use their open book, but the open book, the textbook is unlikely to provide sentences that link quite different terms together. And another way of doing that would be to choose 3 theorems from the course and explain why you think these are significant in the topic in which they appear. So getting them to talk about the role of the theorems rather than trying to prove them or whatever. So I put together a sort of summary of what I think I've been thinking about so far with these ideas, and that is thinking about concepts, procedures, and theorems or properties. The complexity of the topic web is one, and I think even more importantly, the change in the complexity of the topic web over time is one way of gauging the learning that the students are undertaking. It's really important, though, to bear in mind that it's often not until the end of a course or even some years later that students really appreciate what the course was about. When I was in first year, I remember by Christmas, I was beginning to get a sense of what the course was about. In fourth year, some of the courses I appreciated and had a sense of them, and other ones, it didn't happen to me for maybe 2 or 3 years after the final exam. But learning takes time, things take time. So one has to be a little bit careful about making assessments of students as distinct from gauging what's happening for them. So increasing in the complexity of the topic web over time. The richness of their accessible example space. That's a technical term that my wife and I coined. An accessible example space is the space of examples that comes to mind when somebody mentions a particular concept, or arithmetic mean, or line integral. What sorts of examples become available to you as a result of hearing the technical term? And that's, you find out about that by asking them to sketch associated images, by the succinctness of their personal narrative, and by the specific examples that they actually construct. And for the facility with a concept, it seems to me what's really important is the awareness of possible wrinkles, modifications, classic mistakes the concept or the procedure is being used, the concept is being used. So people often complain that students will use a theorem without checking whether the assumptions and the conditions in the theorem actually hold. And this is what I'm addressing here. So one of the things we can be doing is getting students to expose what they think are possible wrinkles or modifications that need to be made when a particular concept is being used. I should have some examples of that in a minute. Under procedure, we have, of course, facility. Are they aware of required assumptions? And are they aware of, again, possible wrinkles and modifications, classic mistakes that they or their colleagues make when they're using that procedure? And again, with theorems or properties, the necessity of assumptions. So the same idea keeps coming up, whether it's to do with a concept, a procedure, or a theorem. The necessity of the assumptions and awareness of where that theorem or that property gets used. So these are all, as it were, domains of possible evaluation or assessment of student performance. Example construction is something that I've thought about a lot. And here's just a few ideas that are associated with that. Getting students to construct examples is quite different from providing examples. The question I usually ask people is, what do you expect students to do with the examples that you give them? And I know from research that many students don't actually know what to do with examples. They try to learn them, or they try and skip over them if they're short of time. And it's within the examples that the inner narrative that we all have that goes with examples, that's all built up by working through examples. So you can ask people to construct an example of an object from the course which satisfies certain constraints. Here's one of my favorites. I know it's nothing to do with any of the courses you'll be teaching, but nevertheless, I like it. If it comes up. Would you please sketch a quadrilateral with exactly one pair of opposite sides equal? I'm confident many of you are imagining it works a lot better if I actually force you to do it on paper, but since you're at a distance, I can't force you to do anything. But if you did do it on paper, that would be an advantage, because I now would like you to do a quadrilateral with two pairs of opposite sides equal. Now, all here I'm illustrating is how you can add constraints. I'm not expecting this to be a challenge. How about this one? A quadrilateral with exactly one pair of opposite sides equal and with exactly one pair of opposite sides perpendicular as well. And then to cap it all, quadrilateral with two pairs of opposite sides equal and with two pairs of opposite sides perpendicular. Now the point here, we haven't got time to work on it. The point here is to start with an object which you think everybody will be, you ask them to construct an object with very, very few constraints, and then you add constraints which force people away from the examples that you think they are going to draw or to construct or to write down. So you use increasing constraints to move people, to shift people, to provoke them to go beyond the example that's familiar. So for primary teachers, if I ask them to draw a quadrilateral, almost everybody draws a rectangle. And so I would, then my next one would be a quadrilateral with at least one angle, not a right angle. That's an example of how I might use what they normally do to force them into thinking beyond the simple examples that they've got. A colleague of mine did her thesis on this example. Construct another integral like this one, which is also zero. The first time that she did this with students, she discovered that people wrote down things and she couldn't work in what way their example was like this one at all. So we add in things like state in what way your example is like, but different from this one. And one of the things we like to do with that is to say, and another, and another. We find that if you do this sort of task periodically, people get used to the fact that you're not going to just ask for one example, but you need another and another. And we find that asking for 2 extra examples tends to make the accessible example space much, much richer. There's a lot to be said about this particular example. Many students don't bother changing the 0 and the 2, the ends of the interval. They simply fiddle with the function. And it suggests that maybe they're not even attending to the limits of the integral, but only to the function. So there's quite a lot to be gained from tasks like this, where you learn what it is students attend to and what it is they may be overlooking. Now, we know what we know is available in this one is to change the interval, to change the function, but keep it linear, change the function altogether, maybe polynomial, maybe trigonometric. So constructing a task like this for students, it's important to review for yourself what you know to be available for them, and then to maybe even prompt them to change the sorts of things that you know could be changed, so that you enrich their example space. This is one of my favorite things to do with tasks. If you take a familiar doing, a familiar task, such as given a function f, suppose we've been told what it is, find the limit of f of x minus f of 3 over x minus 3. It's a routine thing to do. But that can be turned into, by reversing it, what can be said about f if that is the case. So that's a way of tinkering with exercises to turn them into tasks which really probe the student's comprehension of what taking a limit tells you about a function. And I'm quickly going to show you 2 other construction tasks or formats, which I find really, really fun. I think. Oh, no, sorry, this is this one. Okay, so here's some more examples, some more observations about example construction. Choose and solve an example of a problem that can be resolved by use of, and then you can list some procedures from the course, and which shows that you're aware of what can happen when you're using them. For example, partial fractions where a square denominator is required. Construct an example of a problem like this, you display it, which cannot be solved in the same way because of, and you know it's because of some missing condition. Or you can do with multiple uses. Construct an example of a limit problem which requires 3 consecutive uses of L'Hopital's rule. Or construct an example of an integration problem which requires 3 uses of integration by parts, one after over and over and over, in order to resolve. And that will certainly give you some evidence of the richness and the depth of appreciation that students have of those procedures. Here is an example of some course concept. In what ways can this example be modified, extended, generalized, so as to remain an example of the same concept? And in what ways might it be altered so as no longer to be an example? This is a very, very rich source of questions for students to think about. What theorems from the course does this mathematical object illustrate or exemplify? That was this is a general version of the of what concepts is in the course is mod X an example. So I'm going to show you 2 of these. Continuous functions, domain and range. All right, that's elementary constructs, but a lot of students don't really appreciate the relationship between the domain and the range of functions. So in each cell, for example, this cell here, what we're looking for is the sketch or the writing down of the symbolic version of, you may or may not be able to see my mouse, I don't know. Anyway, if x is in the reals and x is always greater than or equal to 0, so that's the domain, that's the largest domain that's possible for it in the reals. And the range of it has to be y, the values of y which are also greater than or equal to 0. So when it says domain, it means this is the largest domain possible in R. And it's quite fun because one of the things you discover is that when you try to put something in one cell, you discover that what you constructed doesn't actually belong there, but it belongs somewhere else, so you can move it over. And another version of this, sketch functions, these are differentiable functions with, let's say, an absolute maximum and it has relative minima. So what you're trying to do is to provoke people into exposing the richness of their example space in terms of what differentiable functions can look like to do with relative and absolute maxima. So now let's have just a little bit of look at proof. The experts in proof, as far as I'm aware, are in Edinburgh in particular, but also probably elsewhere. But here's an example of a task about a proof. Here is a purported proof of theorem 3.6.9.2 or whatever it is. Insert the missing parts. Gaps are clearly indicated. Now, of course, if they can go to their book and copy them. So you might want to not have used exactly the proof that's in the book. You might want to use one that's a little bit different. Or you might say to yourself, well, if they have to turn the pages and find theorem X and then copy it out, maybe they're spending so much time doing that they're not going to do very well on the whole of the examination anyway. But it seems to me, looking at places where there are gaps in proofs, for example, unstated assumptions, and I'm sure that in most textbooks you can find places where there are unstated justifications for the next line of a proof. Why is it necessary in line XX, whatever that, some line number, to show that something is the case? So now what we're doing is we're probing their sense of what proofs are about. What justification can be given for the assertion in line YY that blah, 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 something is the case? And there's a paper by Bickerton and Sanguin, which is very good on this. What is the same and what different about the proofs of theorem X and theorem Y? Where in the proof is the fact that something or other is actually used? So these are all fairly obvious to me ways of probing without simply asking for people to regurgitate a proof. Construct an example for which the proof fails and state why it fails in that case. And so here's an example of tweaking. I asked for some examples from examinations, and I'm going to show you two. So here, physically present, the examination question was state Newton's 3 laws of motion, and there were 5 marks for it. And so one of the tweaks that occurred to me is the following. What is missing or inappropriate in the following versions of Newton's 3 laws? And now you've provided some randomized versions with some misstatements. That's not as hard to do as it sounds. For example, if you take the notion of tangent of a function, a line being tangent to a function, you'll find there are something like a dozen different definitions in different textbooks, not all of them agreeing with each other either. So it's not difficult to, in many cases, to set up a task like this. Or another one here is, for each of the following situations, state which of Newton's 3 laws are acting or need to be assumed in order to make mathematical deductions or to make a coherent mathematical model, if you like. Newton's cradle, there's an assumption in there which well, is necessary in order to allow Newton's laws to tell you anything about a Newton's cradle, and so on. For a three-legged coffee table, what's the workout? You want to work out the forces on the three legs, or indeed for a four-legged coffee table, but thereby hangs a tail. So what I'm thinking about here is ways of taking standard questions that you might ask, which I would call regurgitation questions, and tweaking them so that they could be used online or for open book. And here's a couple of questions from, related questions from complex analysis. They look to me like straightforward computational questions. I need to know how to do that, and I need to do it. And I need to have some idea of how B relates to A. So what occurred to me to do would be to say, what role do the threes play in finding the poles of f of z? Must they be the same? Why or why not? And for the part B, what role does the 3 play in evaluating the integral? And what number might the 3 be changed to in order to require a different method of finding the integral? Seems to me that's probing. Now, I'm confident that many people are going to say to themselves, well, these are much harder questions than the question as posed. But as long as students are attuned to the fact that these are typical of some of the questions that they're going to be asked in order to display their facility or their performance, then it's fair to ask them. Wouldn't be fair to ask them totally blind, as if they've never seen this kind of question before. But it shows me ways in which I can tinker with procedural questions in order to probe comprehension and associations. Right. I'm coming to the end, and I thought it was worthwhile just talking a little bit about validity. A major concern by administrators and colleagues is that the work on an open book may not, or online, may not be that of the named student. Of course, the Open University faced that right from the very beginning and devised various methods of trying to make sure it wasn't too easy to send in a ringer to set the exam for you. Assessment online is open to abuse because students may seek assistance elsewhere. So one, it occurred to me to require students to sign an honesty agreement. And basically what that's saying is that there's no point in getting help with a paper because you're just going to run into trouble in your next year. You could limit the time for working on the assessment to a few hours, 8 or 12 maybe, so that there's little chance of someone getting a response if they do ask for help. Or you could but you've got to make the time long enough for students to fit in with their own caring responsibilities. One of the things we've learned from the effects of the coronavirus and lockdown is that it's really hard when you've got small children or pets or somebody you're a carer for. You may not be able to do things just at a specified time in the day. So you need to make the time sufficiently long so students can fit it in with their other responsibilities. And 3, stressing, this is what I was saying with the 1, stressing to students that the only person they harm is themselves if they seek outside assistance, because they will surely stumble in the next course. And you could provide students with a protocol to use if another student approaches them for assistance. So you could permit a tutorial type supportive questions, but without actually giving answers. Now, that might sound as if it's not finding out what the student themselves can do, but in this day and age, it's not really clear that what a student can do all by themselves under pressure with their adrenaline rushing is actually all that informative. And so I can imagine adopting this in different ways to permit group work, which can then be put in for a group assessment. Anyway, there's lots of literature on that, and I'm not an expert in it. So I've rushed through these various thoughts that I've been having. I hope there's been something there which is of interest. And so what I'd like you to do now is to ask yourself, what has struck you particularly during this session? I'm hoping that you find yourself thinking back over the last hour and asking yourself whether there's something that stands out or stood out at the time, something that maybe you wanted to think about or consider. And if you would be so kind to put a note in the chat while the session continues. And if you want to ask a question about it, then put something in the Q&A section, and we will either try to address them today, or I've promised that after the session, if you want to send observations, comments, and questions to me, that email, then I will endeavor to address them in follow-up notes, which I'll post on both my website and on the Talmo website. So I'm hoping what you're doing is thinking about what has struck you particularly during this session. And just so that you know that there is some follow-up, a possible follow-up, there's my email, my website, or our website. I share it with my wife, Ann Watson, and 2 books. The Mathematics as a Constructive Activity is all about getting learners to generate their own examples. And Mathematics Teaching Practice has over 100 tactics for teaching mathematics based on my Open University experience. And many, but not all, are applicable to online teaching. So I'm going to go back to 18, and I'm going to hand over to Michael to see if we have any questions, answers, questions, comments, and so on. I guess what I have to do is stop sharing, do I? There we go.
Brilliant. Thanks, John. I think virtual round of applause there for, again, for a very thought-provoking session. It was very quiet on the Q&A for a while, but now they're sort of starting to really come in. And I think that there's a couple of questions that talk about, colleagues are asking that they can see how this style of questioning that you're talking about will work for students at the higher end of the ability range. Do you have any thoughts about how it might also apply for students who are not perhaps as able as some of the other students?
Well, the notion of an able student is one that I don't actually understand or comprehend or appreciate. One of the things I've discovered, and lots of other people have discovered the same thing, is that if I go into somebody else's classroom, different people will respond to me. And so the notion of ability is really what, well, let's see, how do I put this? My wife taught me this, to refer to people as previously low attaining rather than as low ability. Because I cannot judge what someone is able to do. I may be able to conjecture some of the things that are accessible to them now. So my answer to the question is yes, these ideas are applicable to all students in all phases of mathematics. Now, clearly some of the questions I've been asking are particularly probing, but getting students to construct examples of things, getting students to have a narrative about what that example actually illustrates, getting students to have a narrative about the relationship between an object, let's say some symbols and diagram, those are all, you can construct those so that they are accessible to anyone who's taking your course, basically. And if they can't answer those questions, I would ask why they're taking your course, or alternatively, what it is you're assuming that they already have facility with, that in fact they don't have facility with, or appreciation and comprehension of. Is that making sense?
It does make sense, John, and I wonder if it ties in with a question that's here from Claudie Carroll, who says that she finds that that their students have a lot of contact hours across all modules, and the maths modules, which perhaps are typically service modules, tend to be very content heavy. So they find that they struggle to have enough time to get through the sort of the main content of basic concepts and techniques. So how do you expose students to that? How do you reconcile this challenge of providing the sort of the core content with the opportunity to expose students to this deeper style of questioning and thinking?
Well, my first reaction is the word cover. The lecturer asks themselves, have I covered all the topics? But what is the metaphor, the image of cover bring up? It sounds to me like somebody painting a wall. Have I covered the entire wall? But it's like a surface phenomenon. Whereas it seems to be much more useful to have students really comprehend and appreciate some of the content that we are demanding of them, rather than expecting that just because I've covered them all, or maybe I've covered them all like with a sheet, but if the students may not have covered them all with a sheet, or that metaphor doesn't work very well because in fact, if you're driving through a whole collection of procedures and concepts, then it is for the students very like a big sheet covering everything, and they get to peek underneath of the sheet a little bit. So my suggestion would be, okay, so my next reaction would be this: how long do you allocate student study time to exercising a procedure that you want them to internalize? Now ask yourself, is there a more efficient way for them to internalize that concept or that procedure than simply doing exercises? So one of my suggestions there would be to ask the student to pick 3 of the items out of this set of exercises, and then construct a narrative which says what's the same and what's different about those. Or how would you know, given those 3, that questions, what does it mean for a question to be like those 3? How would you know, given a question like one of those, that that's the procedure that you ought to use with it? That seems to be just as important as the student doing getting the answers to 25 or 12 or whatever it is routine exercises. So my suggestion is to look very closely at how the students are spending their time. What are they doing with the examples that they're being offered? Do they know what to do with them? Maybe it's worth spending time at the beginning of the course working with the students on what to do with an example. And then as the course progresses, the students may become more efficient at learning because they know what to do with the examples that you're offering. And the same thing with procedures. How do you internalize a procedure? I'm willing to conjecture that very few people listening to this internalized how to do line integrals in complex variables by integrals around closed loops in complex variables by doing 25 examples. I'm confident that most people don't do that. So that's without being able to do some examples, in front of us. That's my best response at the moment.
And I wonder, John, if this sort of ties back to the point you sort of started with, which was getting us to really think about what we were trying to teach and why. And then that sort of ties in with the assessment, and almost, to have this in-depth thinking, we don't have to do it for every single topic in the module. We can think about those critical concepts that we really want students to grasp with, perhaps.
Very definitely. And what I would conjecture is that if you start altering how you work with one particular concept in a course, and probing, allowing, indicating to students how they might study it, what is involved in comprehending it and appreciating it, you might find that over time you can start doing it with another topic as well, and another, and another. That was my experience when I was teaching in the States, that I introduced something for one period and then retreated and did what they were expecting in the others. But I found over a period of time, I was able to work in the way I wanted to more often, and then finish the chapter at the end of the week. So my conjecture would be that if you find something that makes you happier about the student learning, then you will find ways to increase the amount of time you do that and decrease the amount of time you do here's the procedure, here's the concept, now go away and do thou likewise.
There's a related question that comes in from Julia, which I might just slightly alter, but Julia's point is that the tasks you're talking about, sort of like the topic web idea, getting students to construct those, seem quite good for formative tasks, but asks whether or not they're suitable for an exam. Based upon your own experience, and I know you've kind of relayed to me a number of examples where you went through open book assessments, but do you think the fact that if we move away from the sort of 3-hour unseen, sit in a room exam to something that's more extended and open book, does that itself not offer us more kind of possibilities to test student understanding by kind of pushing students on perhaps a bit?
I want to say very definitely. When I think about differential geometry in my 4th year, I don't think I learned anything more about differential geometry from the open book exam. It was a real struggle, real struggle. I think it's very easy to make open book exams very difficult because people are frightened that, they might be able to look through their book and that will enable them to do some of this without actually having to think about it. And my guess would be that as the quotes from Edinburgh and from lots of other places about open book exams, it doesn't, how do I put this? It doesn't help because that I've got an open book exam to make it really difficult. I mean, definitely you want some probing questions for the students to show, some students to show that they really have comprehended and appreciated everything. But you can keep the questions remarkably simple and still students will struggle to do them. I'm confident everybody's found that on 3-hour timed papers. That no matter how simple you make the first question to sort of get them warmed up, there'll be some students who don't do very well on it. And certainly in my experience. So I would not be frightened. I would not be frightened by the open bookness into creating overly challenging problems. But what I hope what I've been indicating is that once you start to ask yourself my opening questions, namely, what do I want students to gain from this course? Then I begin to see that I might need to alter my teaching somewhat. I mean, what I interact with the students about might actually change a little bit. In fact, even quite a lot, to showing them how that a mathematician comprehends a proof, how someone gains facility in using a procedure. And it isn't by doing lots of examples. That's a myth. You gain facility by asking yourself, what is it about that makes this one work? And when I tried it there, it doesn't work. What is it that this procedure is doing for me? And how is it working? It's asking those questions which will give you the facility. All right, if you want to do it against time, that's a different matter. If you want to get everything done in 30 seconds, well, then you have to practice doing things in 30 seconds. But it seems to me open book exams are quite the opposite of that.
There's a number of questions that sort of take that they extend it from the sort of the formative style of assessment to being summative. And then the whole kind of having a standardized mark scheme, and how do you kind of standardize this across multiple markers, and how do you grade these sorts of things have come through in a number of questions. Do you have any thoughts on that one, John, as to how you kind of handle that? How do we actually kind of grade these things if we're using them in a summative manner, this style of kind of testing genuine understanding in our questions?
Well, the place I would go immediately would be to my friend Chris Sanguin and STACK, which is online assessment using with Maple in the background, or computer algebra at least in the background, so that you can ask students to construct an example of something, and they can type in a formula or indicate the example in some standard way, and the machine can test whether or not it really is an example. So they can do a lot of that work can be done automatically. I mean, yes, if you say to people, construct an example of a function that does this, that, and the other thing under this and that constraints, students might come up with all sorts of things. So a marker might feel, oh my heavens, I'm going to have to look at every single one and check whether or not it is an example, and so on. But we have the computer algebra backed systems, so that the machine can do all that kind of checking, and so the marker only needs to look at questions where there's there are sort of a string of words that are necessary, sentences, and they're not hard to mark. I mean, in maths education, that's all we do have is sentences. We don't tend to mark algebra, and it's perfectly possible.
I think sort of last question or so, but a situation that we're all going to face is that students will have had very disrupted prior university experiences in particular this year. And there's a question here from Sally B that says, first year undergraduates following their school experience usually complain that they aren't given enough examples at university. And Sally says that she thinks the real problem is that they don't understand the purpose of examples and then don't know how to kind of internalize them into their understanding using some of your language. How do we begin to change the mindset that it isn't just about staff members giving students examples, but also students identifying their own set of examples?
Well, you do that in class, in sessions with them, whether you're online or physically present. You invite people to construct an example, or you might even say, right, I'm going to construct an example of something or other. You could ask the students to put some constraints on the object, so you don't actually know what those constraints are going to be, but maybe they don't know enough about the topic to be able to do that. Excuse me. The point is that you enact the various things that you want students to be able to offer you as evidence. You enact them with them so that they have experience of doing that. So, okay, take a set of exercises and a bunch of integrals, all to do with substitution, let's say. Method 1, go home and do questions 1, 2, 3, and well, questions 1 to 15 on page 37. Alternative, do as many of the questions on page, whatever it was, 37, as you need to do in order to be able to tell me or tell someone how to do a question of this type. Now, you can then enact that with the students by putting up a set of exercises and saying, I don't feel like doing all those exercises. I want to actually appreciate and comprehend what's behind those exercises. So I'm going to do the first one, the middle one, and the last one. and I'll get you to help me with it. But the question I'm going to ask myself is, what's the same about those? How do they work? What is it what could go wrong? What is there? Do I have to change my thinking a little bit in order to deal with it? I have examples of that, but I think they would take too long to go into. That's the trouble with mathematics. A really good example may be too complicated. May take a little bit of time. So I can't just do it verbally. But yeah. So it's about enacting the actions that you suspect students need to internalize about how to study mathematics. Enacting the things that they need to learn in order to study mathematics, so that they then have some experience, and so that you can then promote them, indicate to them, I'd like you to do this or that or this other action for this homework. So yeah, so I think that's the best I can offer at the moment.
And I think I'll make this the final question,
Okay.
which comes in from an anonymous attendee.
Okay.
Nearly couldn't say that. But it talks about sort of the best, clearest or least ambiguous way to phrase questions. Do you think it's important that we precisely define or phrase questions? So I kind of come at this from a very applied perspective, where I sort of think it's actually quite good for students to struggle with vague, open, ambiguous questions. So, for year one students, I'd use things like, how far can you hit a golf ball? And that's the only question you get. So do you think it's important that we have to be rigorous and precise, or is that part of the kind of the understanding, the problem solving process, where you have to kind of first interpret what the problem may mean?
Well, comes back to my first question, doesn't it? What would you like students to get from this course? If you'd like them to get confidence, self-confidence, personal confidence about being able to deal with how far can you hit a golf ball, then you must have enacted that with them and drawn attention to the fact that you are enacting it. I think that's one of the places where okay, how do I put this? That the people who taught me mathematics might have been a little bit weak, a little bit deficient in indicating how you go about dealing with a question like that. So if, for example, you have a bunch of procedures, a bunch of concepts, and some models, and you build the models and work them through, like all the modeling books that I've ever seen, model after model after model. If you then give them on the exam, how far can you hit a golf ball? You're expecting the students to have done much more with the models than simply follow the reasoning of the model, because you've got to be able to think as a modeler. You've got to actually model. So my question would be to applied mathematicians, are you teaching modeling or are you teaching models? And if you're teaching models, then it's a bit like measure theory for me. I can memorize the 15 of the 45 models that you show me and hope that those are the 15 you're going to ask me about. But I'm not sure that satisfies me or you, frankly. So it's about modeling. Sorry, I shouldn't use that word in the second context. It's about enacting the ways of thinking that you want students to internalize explicitly with them and drawing attention to the fact that that's what you're doing. So I gave up after some years trying to be completely precise about the questions I asked, because I never managed it. There's always somebody in a group who found a different interpretation of what I was saying. And so I've learned to respect that and to value that, even in pure mathematics. That saying, I want to repeat what I've just been saying. It seems to me to be the height of folly to try to be very precise and then suddenly to throw something imprecise at students. Much better to offer yourself some imprecision and then say, oh, gosh, I was thinking about this question and I suddenly realized, I wonder if it means this rather than that. And so indicate that you've got different routes to follow, and to suggest that on an examination, well, you have to decide what your policy is. But the usual policy is something along the lines of, if you follow a route with a problem and it doesn't make it trivial, then that's satisfactory. Okay, what's trivial? The definition of trivial is going to change. I can't give you a definition of that. But that seems to me a reasonable rubric for students, where they interpret a question differently from the way the examiner posed it or intended it to be. The examiner really has a responsibility to follow through any variation. So in thinking about this question, it seems to me that it's valuable to offer a variety of, as precise as you can. Maybe you can be totally precise. I can't. Somewhat imprecise, deliberately imprecise, and really wide open, like the golf ball. It seems to me that the wide open golf ball question is much more suitable for a project over a whole term than for 3 hours or even overnight or even for a week when people are locked down at home. But that's just my opinion. I can imagine people would have different stances towards that. Yeah.
I'm glad you said that, John, because that was actually a project over a couple of weeks. Right. So that is reassuring that I did something right. But I think we'll end it there. I mean, I really think, John, that was a wonderful session, where I think what you've really highlighted is that we really cannot divorce the assessment from the learning and what we in particular want the students to learn and what we want students to understand. And sometimes we perhaps just think about how can we adapt assessments, but actually thinking about why we're assessing things that we are in the first place. And so I think that, again, you've done exactly what I thought you would, which is get the thoughts going through my head as to how we begin to think about these things. And one wonderful idea that I pulled out that I did have a bit of advance insight having spoken to you is the idea of the topic webs, because for students, they can sometimes view topics as just being discrete entities, but actually the topic webs give us the chance to connect different topics through the webs. And actually you can build this collection of understanding as well. So I think, John, I think that was a brilliant session. I think you've got everybody thinking. I'm seeing some of the comments that are coming in and a number of the questions. I think you've done an absolutely brilliant job today. I see Rachel and Kevin have joined me back on the screen, and for the virtual round of applause, John, and just to say on behalf of Talmo and everyone, thanks for such a wonderful job.
Thank you very much for the opportunity, and I look forward to seeing the video.
Thank you very much. Thanks. And thanks to everybody for coming.
Yes, thank you, everyone. Anybody who came. Wow, fantastic. I hope it was useful for somebody.
I think everyone who was here really had a treat. So thanks, John.
Good.
Yeah, thanks ever so much, John. It was certainly useful for me anyway. So that's one person.
Well, and me, so that's two. So
that's two. Well,
and
Kevin, so there you go. That that's
sorted then.
We can see people saying thanks in the chat. So there we go. Right. Okay. Shall we stop the recording?
You can stop the recording now.
We'll allow people to leave.